Hello, good afternoon or good morning, depending where you are, and welcome to this webinar on Harbours structural health monitoring. I'm Daniele Inaudi from SMARTEC, and today we have the pleasure to have a guest for this presentation, our distributor, Martin Veldhuis from Inventec in the Netherlands, and he will share with us his experience and his company experience in using fiber optic structural monitoring systems for the monitoring of harbor structures. So without further ado, I will hand it over to Martin for his interesting presentation.
Well, thank you for the introduction, Daniele. My name is Martin Veldhuis of Inventec in the Netherlands. We have a lot of experience in structural health monitoring systems for key walls, and I would like to tell you some more about this. All sensors are based on fiber optic technology because of their accuracy, reliability and durability. The sensors are permanently integrated into the structure and remain operational throughout the lifespan of the structure as such. For all these applications we have installed sensors manufactured by SMARTEC and Rockhest. First of all, I would like to show a general picture of the parameters that are useful to monitor for a key wall. Later on in this presentation, the individual sensors will be discussed into more detail. Now, coming to the general picture, this is a schematic cross-section of a typical key wall in the Rotterdam port area. Showing the phenomena that could deserve permanent monitoring. Now, first of all, we're talking about erosion of the soil behind the retaining structure. The desoiling can occur, for instance, by an opening in the sheet piling or a leak in the case of a diaphragm wall. Then, secondly, that's a quite obvious one, deformation of the retaining wall. I think this speaks for itself. In the third place, monitoring the anchor forces on the grout anchors that retain the structure can be done by installing sensors into the hollow core of the grout anchors. Further, it can be very useful to monitor the loads on the key wall structure, in particular for general cargo or mixed cargo terminals. Experience has shown that cargo tends to be stacked up much higher than it should be, and as a consequence, the actual load exerted on the structure can exceed the design loads. That just happens in practice. The same obviously accounts for the area behind the key wall. We will also talk about that later on. And last but not least, of course, the groundwater level in relation to the harbor water level represents an important semi-dynamic load on the whole of the key structure. On the next slide, it is interesting to ask yourself the question: well, why should you monitor a key wall? Generally, there are a couple of reasons that are quite common for structural monitoring, like it gives insight into structural condition, it reveals design or construction errors in a timely manner, and it enhances the knowledge on structural behavior. But there are a couple of things that are in particular of interest for key walls, and that is in particular discovers deficiencies that develop with time. This in particular for key walls is a tool for scheduling preventive maintenance with the aim of extending the lifespan of the structure and to save on the total cost of ownership. when you start monitoring it, when something is really happening, then everyone knows that the costs are much higher, and you may still not get the right picture. Then it shows hidden reserves. That is also of interest for key walls. During the life of a key wall, its purpose, its service may change. For instance, an ore terminal may become a container terminal, and then there's the question, can it withstand a load that it has not been designed for originally? And it can be hard to determine this if you lack the historical structural behavior of the key wall. And then the operational use of the terminal is also important for the owner, because the owner is interested to keep an eye on how his key wall is being treated by the company that is using it. And he wants to know whether the structure is about to be loaded in excess of the design load, and get a remote warning whenever that happens. And finally, assessment of liability. What happens in case of a calamity? Is it the consulting engineer that provided the faulty design? Is it the contractor who did a bad job, or is it maybe the user that mistreated the asset? It will be hard to tell, of course, without having a proper monitoring history. And if the port authority doesn't have that, they totally remain in the dark as to why something has happened. Now I would like to go into more detail on the individual monitoring applications. First of all, the potential erosion of the subsoil behind the key wall. What we apply for this monitoring phenomenon is distributed strain sensing along an optical fiber. Well, for most of you, it will be clear how this works. It's basically it's such that a reading unit constantly enlarges a high frequency pulse of light into of a particular wavelength into an optical fiber, and measures the shift of the so-called Brima frequency in the backscattered light. If there is a strain on any point in the fiber, the Brima frequency or wavelength changes, and this change has a mathematical relation to the actual strain that is occurring at that point in time, that point along the fiber. Of course, that phenomenon occurs over the whole length of the fiber, and as a result, you get this truly distributed strain, as shown in the picture at the bottom. And what now happens in actual fact is that the fiber is dug into is installed in the soil behind the key wall, and the strain is a measure for the subsidence of collapse of the soil, or for the erosion. And you see that typically in this case here you see apparent increase of the strain, local strain, and that is a clear indication that there's a major subsidence in the soil behind the key wall, which may have been caused by erosion. This is a true picture of one of the key walls that we installed in the one of the monitoring systems that we installed in the port of Rotterdam, and this is a key that is 550 meters long. At the spatial resolution of 1 meter, so you have the equivalent of 550 spot sensors, and this gives with an accuracy of 1 meter where the corrosion, erosion of the subsidence is happening. And this is how it looks into practice. There are two ways of let's say, installing the fiber. That is, you can take a couple of fiber cables, but you can also use an optical fiber that is integrated in the geotextile, which has the additional advantage that it is stronger. The geotextile retains the force, so the fiber does not break even in with larger major collapses of the soil. You see here where we install the fibers. They are installed underneath the structure, but behind the retaining structure. Now you could say, well, is this such a big issue? Should we really do that? But I think these pictures that are actually taken from the subsidence of key wall in the Rotterdam area shows that erosion monitoring is absolutely not an unnecessary luxury. This is, by the way, this is not an old key wall. It was a key wall that had been completed 4 months before. So even in an early stage, these things can easily happen. And the importance of an early notification of a subsidence is, of course, that you want to avoid major catastrophes. When if you don't have a monitoring system, the erosion and the desoiling progresses and can cause a major collapse on the surface of the turbine. For a visualization of the software, we normally use DiView, which is a software package that has been developed by SMARTEC, and it can be used to easily visualize in real time where critical events may be taking place along the length of an erosion monitoring system. Now to anchor forces. This picture shows a typical grout injection anchor as it is widely used for key walls. After the anchor has been drilled in place and the grout has been injected to provide the anchor force retaining grout body, the anchor is flushed clean over the required depth, and the strain sensor is placed concentrically into the hollow core of the anchor. And then subsequently the core of the anchor is grouted up with non-shrinking grout. Now after hardening, the grout serves to transfer the strain from the anchor to the sensor. For the measurement of the pulling force of the anchor, the sensor is typically placed at a relatively short distance behind the anchor bolt, because at that location the anchor is free to move, to strain. As the friction with the surrounding soil is negligible, so that a true relation between strain and force can be established. The type of sensor we use for anchor monitoring is based on Bragg rating. I assume that the people in the audience have sufficient knowledge to understand how that operates. So I will not go into further detail about that. Multiplexing will also be a known possibility of FPG sensors. Measuring this FBGs at varying temperatures, which you also have with anchors, grout anchors, is that the shifting of the back reflected wavelengths is caused by both strain. Sorry. I have to go. No, I have to go back. Yeah. The shifting of the back reflected wavelengths is caused by both strain and temperature changes. So you need to have two FBGs in line, one that is relaxed and one that is pre-stressed. The relaxed one only measures temperature, so that you know how much you have to compensate for the sensor that measures both strain and temperature. Now, the point is that the acid donor obviously is not interested in strain, but wants to see the actual force that is exerted on the anchor. And the conversion of strain into force is done during the tensioning of the anchors in the field. During the subsequent tensioning stages, the strain sensor and the temperature sensor are read out, at the same time marking the force readings from the tensioning jack. This then establishes the relation between the strain and the force at the time and the circumstances of the tensioning of the anchor. But of course, in the software, the measured strain has to be compensated by the reading of the temperature sensor, and of course also the turbo expansion or shrinkage, as the case may be, of the material of the anchor, so the steel expansion or shrinkage. And that is an exercise that has to be done before it can be made operational. For economical reasons, not all anchors will be fitted with a sensor measuring the forces of only a representative number of anchors along the length of the keywall will give a representative picture of what is actually happening. Now we are going to the load of the superstructure. Now this picture shows an example as to how the superimposed load on the keywall can be monitored. The idea is to mount strain sensors into a number of the foundation piles, and these sensors measure the compression, or better the additional compression of the pile heads caused by the superimposed load. Calibration is done in the field. You see here this is the lean concrete floor that has already been laid for the superstructure. This is the pile head, and this is the hole that has been drilled into it in order to receive the sensor, and afterwards this is grouted up again. Calibration is done in the fields by putting known weights on the superstructure and taking the strain reading from the sensors. And as with the anchor force sensors, also here the strain readings obviously are compensated for changes in temperature. And here also a representative number of sensor containing piles will be sufficient to give the adequate information of how the key is loaded. And the Port Authority receives an alert or alarm whenever preset levels are reached. Now, load on the area behind the key wall. Well, this is generally achieved by installing a number of total pressure cells divided over the stocking area, which you see here being installed. Even these TPCs are of a fiber optic execution. Also again for a number of good reasons. They are very durable. They do not need any recalibration ever after the initial calibration. And they are insensitive to electromagnetic induction. The one-time calibration, again, is done by putting known weight on the terrain, on the surface, and taking the respective readings. Ground water level and harbor water level. As I already remarked in the introduction, water pressure is an important variable load on the key structure, and particularly in tidal areas as we have in the Netherlands. Both the groundwater level can change in itself, but also the tidal effect can be very important. In Rotterdam, you're talking about 2.5 meters. And it is, from a structural monitoring point of view, it is important to incorporate these parameters into the overall monitoring picture. Normally these are piezometers that are put in standpipes, both in the area behind the key wall and the harbor. Deformation of the retaining wall. There are basically two effective technologies to monitor the deformation of the retaining wall. Now, first of all, what you see here is the only non-fiber optic solution presented in this webinar, and it is the shape accelerate field, or shorter the SAF. Now, this SAF, as we call it, consists of an articulated chain of MEMS inclinometers, which can be installed in a hollow tubular pipe that is welded to a steel retaining wall, or which can also be put in a PVC pipe that is incorporated, cast into the diaphragm wall. And what the SAP does, it provides a direct presentation of the shape of the retaining wall over time, which you see here in a more precise picture. The operation, this gives the operating principle of the SAF. It's built up from a number of segments that each contain a biaxial MEMS inclinometer, and these segments are all interconnected in such a way that they can rotate in all directions in relation to one another. And it has a diameter of only 25 millimeters, which actually makes it possible to install it anywhere. And it fits into a pipe of only 30 millimeters in diameter. In this way you get the exact distributed deformation picture in both X and Y direction, and the total movements of the harbor water are clearly reflected in the deformation cycles of the retaining wall. So that means that you see the key wall, you see it moving already during a cycle of 2.5 meters tidal movement. The second possibility is when you have a diaphragm wall, it is easy to fit the rebar cage with sensors. These generally also can be FPG sensors. They are attached to the rebars, obviously as far as possible from the neutral plane of the cross section. And if you have a number of these FPG sensors in series, you can compute from that the deformation, the shape of the retaining wall at any moment in time. Data infrastructure and data management, not unimportant, of course. The case is, this is a typical flow schedule showing the data management infrastructure that we provide. The sensors are interrogated by their respective reading unit, and that are located in the control room at the end of the key wall. And from there, the data are pushed to a remote server that runs on our web application that we have given the name LiveSense. Now, the asset owner can log into this web application as he likes at any moment in time to view the structural behavior of the key wall. LiveSense is also programmed to store data in a format and an archiving policy as agreed with the port authority. And whenever a preset alarm, a preset value of any of these sensors is arrived or is reached, the direct alarm goes from the local control room to the asset owner. So he can, if he wishes, he can take the applicable measures. For instance, he can call the user of the terminal and say, hey, you are overloading my key, you're stacking your goods too high. Now I've come almost to the end of the story. Why measure with light? This is something that is normally included in this presentation. Because we often deal with people who are not familiar with it, but it will sound quite familiar in the ears of the people in the audience at this moment. Of course, it gives truly distributed measurements. It's unrivaled accuracy and resolution, no drift, no loss of signal. You can tens of kilometers without any booster or intermediary reading unit. Measurements are not affected by electromagnetic induction, insensitive to a lot of evil things, very small size, minimal quantity of cabling, as I have already explained, unequal durability, and intrinsically safe, so it can even be applied in hazardous areas. Well, by this I have come to the end of my short presentation. I hope you found it useful, and if you have any questions, I'll be pleased to answer those.
Okay, thank you very much, Martin, for this very interesting presentation. If anybody in the audience has any question for Martin, you can use the question panel that you will find on the right-hand side of your screen. You can type your question there, and I will relay it to Martin, or we will answer in private later on. Maybe I can start with a quick question myself. I was wondering how you typically separate responsibility between your company and the end user in terms of data management, management of the alarms, and also maintenance of the system.
Well, basically, the end user, and that is in our cases, yeah, it's, I would say the asset owner generally is also the end user, and the asset owner puts his requirements on paper, and we design a system that fulfills those requirements. And the responsibilities. Well, if there's a sensor not working, it will show immediately in the software. Basically, that is the let's say the borderline of the responsibility.
Okay.
If you want to make your question more specific.
I think it was also related maybe to thresholds and reacting to alerts. That's done directly by the end user, if I understand correctly.
That's correct, yes. Yeah, we do not take over the operational follow-up of the monitoring system as such. That is totally due to the client. What we do, however, is we do general inspections, periodical inspections, which is normally once per quarter year, in order to see whether everything still on the site works okay. One particular thing, it's a small silly thing, but it just happens is that when you have a piezometer hanging in harbor water, which is basically salt water, you have all sorts of animals that like to stick to attach themselves to the center, also you know, shells and all that, sea pods, and all those animals, and that requires just a bit of maintenance, and that is done during these quarterly inspections.
Okay. We have another question here about the desoiling application. What happens when you detect one of these holes? What is the reaction of the owner?
What the reaction of the owner is, in any case, it has to be stopped. That means that there are a couple of remedial possibilities. First of all, what generally happens is that they put divers in order to inspect the outside of the keyhole structure at the location of the subsidence that has been indicated. If they can find something, they will repair it. For instance, if you have a sheet piling that has run out of its key, then divers can see that, and okay, they can repair it, they can close it. The second remedial possibility is to make a stabilization of the soil behind the key wall by means of grout injection. That is a possibility. The asset owner may decide to do so. Whether or not, in both cases, the cause of the desoiling may have been detected. So those are a couple of measures that the owner generally will take.
Okay, so thank you very much again. It was a very interesting presentation. And if anybody has further questions, please drop us an email, and we will soon post also this presentation online. So thank you all for attending. Bye-bye.
Okay, bye-bye.